Hello everyone. Are my slides are visible to all of you? Please confirm so we can start.
Yes, sir.
Okay, thanks a lot. So a very good evening to all of you again. So today we are going to have this week 8 live session of the biochemistry. Here we'll be taking few problems and solving them. This will help you to solve the assignments and will make you more understand about the biochemistry course, right? So let's begin with the first problem. Let me see everything is fine. Nothing fine, everything. So first problem is which one of the following methods can be used to solve protein structure? Any one of you? Yes, please answer.
First and second.
First and second. X-ray crystallography and NMR spectroscopy. Okay. Why not third? Yes, you are right. First and second. Okay, let me admit the people who want to write late. So option D is correct, right? Yes. This Leventhal's protein folding paradox conclude that the protein folding to its native conformational structure happens by a random search through all the enormously large number of possible structures. It happens spontaneously by random search through some specific number of possible structure after some million year of time. So according to this Leventhal protein folding paradox, the protein folding to its native conformational structure when it happens. What do you guys think? Any one of you? Any one of you? So according to this, it happens spontaneously. So let's see what are the this Leventhal protein folding paradox. This Leventhal protein paradox is that finding the native folded state of a protein by random search among all possible configuration can take an enormously long time. It proteins can fold in seconds or less. So mathematical analysis of a simple model shows that a small and physical reasonable energy bias against locally unfavorable configurations of the order of few kt can reduce Lewinthal's time to biologically significant size. So, for example, a polypeptide of 100 residue will have 99 peptide bond, right? And therefore 198 different pi and psi bond angles. If each of these bond angles can be uh, if each of these bond angle can be in one of three stable conformation. See here conformation. Uh, the protein may misfold into maximum of 3 is to 198. So 3 is to 198 different conformation, but still it fold into one conformation simultaneously. Okay. So on the next is hydropathy plot is a graphical display of local of amino acid side chain in a protein. It's hydrophobicity, hydrophilicity, electronegativity, nucleophilicity. So hydropathy plot is for what? Hydropathy plot is used for what? Yeah, actually, if it text to me, will not be able to see because my screen is on presentation mode. So it will be better if we speak. Yes, Rinku. A. So it will be better if we speak because I have to come back to see that text. It won't be possible. So option A is correct, right? So it is for local hydrophobicity, right? So hydrophilicity clause is quantitative analysis of degree of hydrophobicity and hydrophilicity of amino acids of a protein. It is used to characterize and identify the possible structure or domain of the protein. In a sliding window approach for making a hydropathy plot for membrane protein, which of the following statement is incorrect? First statement says a small window produces Neusser plot. A small window reflects high local hydrophobicity. A window of 10 is optimal. A optimal value of window is in range of 9 to 11. Which one will be the correct option? So according to sliding window approach, option A, B, and D is correct. So a small window produces Neusser plot. A small window reflects high local hydrophobicity. Optimal value of window is range from 9 to 11. Optimal is not 10. So this hydropathy plot is also termed as hydrophobicity or hydrophilicity plots. Hydropathy plots are designed to display the distribution of polar and non-polar residue among protein sequence. This analysis has the goal of predicting membrane spanning segments or transmembrane proteins which are highly hydrophobic or regions that are likely exposed on the surface of the protein, which have hydrophobic domains and therefore potentially antigenic. Several skills of hydrophobicity have been developed, most of which were derived from the experimental studies on uh, mm, this partitioning of peptides in nonpolar and polar solvent. Two of the most commonly used hydrophobicity index are incorporated into the hydrophobicity analysis is Skye Doolittle and Hooke scale. So there are two scales. First one is a hydropathic region achieve a positive value with hydrophobic value achieve negative values. These two are scales are given here. So next question we have for an alpha helix, what would be the number of amino acid residue required to span a membrane of 30 angstrom? So for an alpha helix, what would be the number of amino acid residue required to span a membrane of 30 angstrom? Anyone? Anyone of you? So option A is correct. So 20. So these transmembrane domains are usually alpha helices. A length of alpha helix sufficient to span a usual width of a lipid bilayer requires 18 to 21 amino acids. So membrane spanning domains are typically made of around 20 hydrophobic amino acids in alpha helix conformation. This is sufficient to span 30 angstrom hydrophobic core of a model lipid bilayer, as each amino acid contribute to 1.5 angstrom to length of a helix. So basically, one amino acid contribute to 1.5 angstrom to the length of the helix. So if it is required for 30, right? So 1.5. If you require 30, then the number of amino acid it will be 20. Fine. So next is what is the dihedral angle of alpha helix? So the average length of an alpha helix is 10 residue, uh, as taken from surveys of this structural database. The average dihedral angles phi and size minus 64 plus minus 7 minus 41 plus minus 7. Also obtained from this survey are found to differ slightly from geometrically pure alpha helix. So this geometrically pure alpha helix phi and psi angles are minus 57.8 and 47. Next question we have to construct a helical wheel for an alpha helix for a specific amino acid sequence. What should be the degree of rotation per amino acid? For making the helical wheel, what should be the degree of rotation for a specific amino acid sequence? Okay, it should be 100. Why it's 100? There are 3.6 residue turn in an alpha helix. So in each and every turn, there are 3 points average 3.6. Yeah, 3.6 are average number of residue per turn in an alpha helix. So which means that there is one residue every 100 degree of rotation. So 360 divided by 3.6 is equal to 100. So option 100 is correct. So from the basic understanding of alpha helix helical structure determined by Corey, Pauling and Ramchandran, we know that the complete helical turn, which means 360-degree rotation. So complete helical turn is 360-degree rotation, is obtained within a span of 3.6 residue. Yes. So 100-degree rotation is required for making this to construct a helical wheel. Fine. So under the normal circumstances, a protein will not denature by. Answer this question. Anyone of you? Yeah, we are connected. So answer this question. Under normal conditions, protein will not denatured by sodium dodecyl sulfate, heating to 90 degrees centigrade, hydroacetic acid, urea, which will not lead to denaturation of the protein.
C.
Hydroacetic acid. Okay, YA, B, and D. Let's talk about means what's denaturation, why these elements will lead to denaturation. So, what do you mean by denaturation? Yes, what do you mean by denaturation?
Conformational change in structure of protein.
Conformational change in structural proteins. Okay, that's a fancy word, but what on the means if you see on the from the perspective of chemistry, what are the changes are there which lead to the which are called denaturation? Means is there any changing in term of bonds, interactions, which kind of interactions are perturbed or altered, which kind of bonds are disturbed, so that is leading to denaturation. So if we understand on at the molecular level of the proteins, okay, let's say we have sodium dodecyl sulfate, it's a surfactant, right? And then what it will do, how it will denature, which kind of bond it will disturb. I hope this it will make more us more clear. Okay, if you see any reagent, okay, this reagent what can do with the protein, which kind of bond it can form with the protein, so whether it will denature or not. So primary, secondary, and tertiary, right? And quaternary. Primary, secondary, tertiary, and quaternary structure. So denaturation means disturbing the bonds or forces here, interactions in secondary, tertiary, and quaternary. So sodium doxyl sulfate, sulfate, it will and it will disturb the hydrogen bonding network, right? Electrostatic interactions, salt bridges, it will disturb that. This heating to 90 degree, this it will disturb this hydrogen bonding network, and then if hydrogen bonding network in the protein is disturbed, then the denaturation will happen. Means its folding will uh, be towards linear side, right? So secondary, tertiary, and quaternary interactions or quaternary structure of the protein will be perturbed. Same as urea. So why urea is a denaturing agent? What is there in urea? This let me draw. This is H. This is urea, right? Urea is known to form a very strong hydrogen bonding. So urea will destroy all the hydrogen bonding between side chains and uh, backbone, and it will disturb and it will form itself hydrogen bonding. So it will denature the protein completely. Whereas isostatic acid, what is isostatic acid? Isostatic acid is something this, right? So it is a alkylating reagent. It will not denature the protein. So option C is correct, right? Option C is correct. Okay, this another question we have. This Chow-Fasman parameter are useful in solving which kind of structure of protein? Primary, secondary, tertiary, or quaternary? Any one of you? This Chow-Fasman parameters.
Option B.
Secondary structure. Yes, you're right. So the Chow-Fasman method predicts helices and strands in similar fashion. First, searching linearly through the sequence for nucleation region of high helix or strand probability, and then extending the region until a subsequent force residue window carries a possibility of less than one. So this Chow-Fasman method has been widely used for predicting protein secondary structure. It is based on knowledge of the potential amino acid residue from alpha helix to beta sheet region in proteins. So option B is correct, right? In sequence of amino acids, 4 out of 6 amino acids have a Chow-Fasman parameter P is greater than 100. This sequence of 6 residues is expected to form an alpha helix, beta sheet, or turn of beta sheet or so that is last question is related to like this Chow-Fasman parameter. They find this secondary structure. That means formation of alpha helix, beta sheets, or with or tunnel, right? So if this 4 out of 6 amino acids have Chow-Fasman parameter greater than 100, then this sequence of recipe will expected to form of an alpha helix, a beta sheet or turn, or a beta sheet or turn. So for knowing this, we should know the Chow-Fasman parameters. So it will form an alpha helix, but how? So current these are the parameters have been given by the Chow-Fasman. Um, Assign all the resident peptide an appropriate set of parameters. Scan through the peptide and identify regions where 4 out of 6 contagious residue have P alpha helix greater than 1. That region is declared by alpha helix. Extend the alpha helix in both directions until a set of four contagious residue that have average p alpha helix less than 100 reached. That is declared the end of the alpha helix. So here are like different parameters of the Stokes-Felsman is given. So according to that, it will form alpha helix. So okay, since it's given already here, this collagen is a type of fibrous protein, globular protein, or transparent protein, or cytosolic proteins. It's a fibrous protein. It is the most abundant proteins in animal. This fibrous structural protein comprises a right-handed bundle of three parallel left-handed polyproline second type of helices. Much progress has been made. Okay, so it is a fibrous protein. So what is commonly used to disrupt the disulfide bond in proteins? Urea, sodium chloride, 2-mercaptoethanol, and anhydride. What it is? What is commonly used to disrupt the disulfide bond in proteins? Urea, sodium chloride, 2-mercaptoethanol, or anhydride.
Mercaptoethanol.
Okay. So urea, what it will do? Denaturation. Any effect of sodium chloride on the protein?
Yes,
What will be the effect?
on ionic bond, effect on ionic bonds.
Effect of ionic bonds, but as a practical, we do also work on the proteins. So what we observed that if we increase the concentration of sodium chloride or salt in into the buffer, then it enhance the solubility. So to mark up to ethanol, how it will disrupt the disulfide bond in protein, and what's the anhydride role? Means what is the anhydride? Okay, so yes, it is to mark up to ethanol. So it will disrupt this disulfide bonds in proteins.
Ninhydrin act with amino acid
Mm-hmm.
and forms purple color.
Yeah. So amino acids, it will form with the alpha amine or epsilon amine, right? It do not react with all the amino acids, but if it is in free form, it will react. Otherwise, it will react with amines. So this is the dinohydrin structure here. Lab amine, it will react with this dinohydrin from this kind of complex. It will give to the purple color. And if it is proline, it will give this orange product. However, this disulfide, this beta mercaptoethanol, let's say it is beta mercaptoethanol, then it will reduce this disulfide. This is disulfide. First, the sulfur will attack here, it will go, and then it will form the bonds between this the sulfide, and then it will reduce it. So this is how it will reduce disulfide. Okay, next question we have, which of the thermodynamic parameter is destabilizing in nature with respect to protein folding? Delta G, delta S, delta H. Gibbs free energy, entropy, enthalpy. Change in Gibbs free energy, change in entropy, change in enthalpy. Which are the two parameters which are destabilizing in nature?
Delta G and delta H.
Delta G and delta H.
No, 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 no.
Okay, it is only with the protein folding. This delta entropy will be destabilizing. Other will be stabilizing. Okay, which of the following energy terms does not contribute to the covalent component of energy in protein structure? Stretching energy, bending energy, torsional energy, or Coulomb energy? So, in protein structures, which kind of forces are not involved, or which kind of bonding energies? These kind, all the energies, you might have put it in the IR: stretching frequency, bending torsionals, and Coulomb energy in physics, Coulombic forces. So this Coulombic energy is not contribute to the covalent component of energy in protein structure. It will contribute to the ionic bonds, salt bridges, and where this stretching, these all are related to IR frequencies, right? Stretching energy, bending energy, torsional energies, and its Coulombic energy. It's for the ionic bonds. So it will not contribute to the covalent component of energy in the protein structure. Fine. A process by which a protein structure assumes its functional shape or conformation is commonly referred to as denaturation, folding, synthesis, hydrolysis. I'm repeating: a process by which a protein structure assumes its functional shape or conformation is commonly referred to as
Tin folding.
protein folding. Yes, you are right.
सर वो थर्मोडायनामिक पैरामीटर का क्या था?
ओके, थर्मोडायनामिक पैरामीटर्स का जो उसका एंट्रोपी होगा,
Yes, sir. I also not getting.
okay, so like once once the protein folding, right, will be there, right, then it is asking which thermodynamic parameter is destabilizing in nature. So Gibbs free energy, it will be destabilizing, and this enthalpy, it will be stabilizing. However, this entropy, delta S, change in delta S, will be destabilizing.
तो
So
सर 2 और 3
yes,
2 और 3 है ना सर?
2 or 3, no del, not 2 or 3. Are you seeing the correct slide where I'm presenting, or it is there any?
Yes, yes, sir.
So, so this destabilizing parameter, it will be delta S. So why it will be complete reason, I can get you back again, and means I can look into details and then I'll be able to answer you, means make you understand completely.
Okay, thank you, sir.
Okay, thank you. So let's say if you have any doubt regarding any questions further, you can drop me an email. You guys might be having my emails. You can drop an email. A non-protein part of an enzyme is known as coenzyme, vitamin, enzyme, or prosthetic group.
Prosthetic group.
Yes, it is prosthetic group. So next we have a class of enzyme that catalyze synthetic reaction where two molecules are joined together and ATP is used, is hydrolase, lyase, ligase, isomerase.
Ligase.
I guess yes, ligase. The benefit of measuring the initial rate of reaction V naught is that the beginning of the reaction in at the beginning of the reaction ES complex ES complex is such as E enzyme plus substrate, this making this is complex, leading to the final product plus enzyme. In this ES complex, concentration of ES complex can be measured accurately. Change in S, okay. The change in S substrate concentration are negligible. So S can be treated as a constant. Changes in Km are negligible, so Km can be treated as a constant, or V naught is equal to V max. So benefit. So it is asking why we measure the initial rate of the reaction V naught. So let's say once we calculate the rate of the reaction, so why we consider at the rate determining step initial rate of the reaction. So we measure V naught, right? V naught is equal to V max into Km. Okay. Now V max into substrate concentration plus Km into substrate concentration, right? So we measure V naught. So it is asking what is the benefit of measuring the V naught. So what is the benefit of measuring the initial rate of the reaction? Which option is correct? Any one of you? It is again from enzyme kinetics.
Km कांस्टेंट होता है सर.
क्या कांस्टेंट होता है? Km कांस्टेंट होता है.
माइकलस मेंटेन कांस्टेंट.
Yes. So it is a constant. Uh, no, what I think that once why we measure the rate of the reaction at the initial rates, at the initial point, because the change in the substrate concentration, it will be very minimal, right? So change like enzyme kinetics, if we have a concentration of 100 millimolar of the substrate and it is getting converted over the period to the product, so the change into the concentration of substrate, right, it will be very minimal. So the change in substrate concentration can be treated as a constant. So that's what initial rates are.
कैलकुलेबल हो जाएगा. कांस्टेंट है तो कैलकुलेबल हो जाएगा.
Yes. So next question we have, turnover number of enzyme is dependent upon size of enzyme, molecular weight of enzyme, active sites, concentration of substrate. What will be the correct answer for the turnover number?
Concentration of substrate.
It will be dependent on the active sites.
So more enzyme, more active sites. So turnover number is more.
Yes. So this again quotient theory of enzyme exchange is reduced to fit theory, lock and key theory, induced fit theory, enzyme coenzyme theory. So it is induced fit theory. Option C is correct here. Another question is, Michaelis and maintain assume that the overall reaction of for enzyme catalyzed reaction could be written as, it's a E plus S gives to this equation. In this reaction, the rate of breakdown of enzyme substrate complex can be described by the expression. So they are asking the rate of breakdown of enzyme substrate complex can be described by the expression. So this
Option D.
option D, K minus ES K2 ES. So it is asking that this and this it will get breakdown into two ways, right? Whether in this direction, formation of enzyme plus substrate, or whether in this direction, formation of enzyme plus product. So option D is correct. Okay, how do you get option D?
K2 for reverse reaction from product to enzyme substrate complex, and K minus 1 is also reversible.
Okay, so from the rate of the reaction, so if rate of the reaction is directly proportional to substrate concentration, right? So if you want to rate of the reaction, it's R. Rate of the reaction is equal to K into substrate concentration, right? Here substrate concentration is ES, right? And total rate of the reaction will be this. For like backward reaction, it will be R is equal to K minus 1 into ES plus conversion to the product, it will be K2 into ES. Yes. So this, okay, this will be overall reaction of for enzyme. I mean this breakdown of enzyme substrate complex. Great. Fine. So option D is correct. Another question we have, a small molecule that decreases the activity of an enzyme by binding to a site other than the catalytic site is termed as allostatic inhibitor, alternative inhibitor, competitive inhibitor, or stereospecific inhibitor.
Allosteric.
Allosteric inhibitor.
Allostatic inhibitor. Yes. Okay, pepsin and urease are example for which class of enzyme? Hydrolase, ligase, oxidoreductase, lyase. So it asking the
Hydrolases.
yes hydrolases. Compare next we have compare the two reaction coordinate diagram below and select the answer that correctly describe their relationship. In each case, a single intermediate is the ES complex. Okay, so option A says A describe strict lock and key model, whereas B describe a transition state complementary model. Okay, B option says activation energy for catalyzed reaction is 5 in A and 7 in B. Okay, the activation energy for uncatalyzed reaction is given by 5 plus 6 in A and 7 plus 4 in B. The contribution of binding energy is given by 5 in A and 7 in B. So here the option A is correct. The first one is describe the strict lock and key model, whereas B describes a transition state complementary model. So these are the reaction coordinates for this free energy and I mean plots for the enzyme inhibition. Okay. So next we have the active site of an enzyme differ from an antibody antigen binding site in that the enzyme active site contains modified amino acids, catalyze a chemical reaction, is complementary to a specific ligand. None of the above is correct. The question again says the active site of an enzyme differ from an antibody antigen binding site in that the enzyme active site contains modified amino acids, catalyze a chemical reaction, is complementary to specific ligand. None of the above is correct. So it is asking this how this antibody antigen binding site, how the active site of enzyme, how it is different to antibody antigen binding site. So what do you think? What is different between enzymes active sites and antibody antigen binding sites? They contains modified amino acids or catalyze chemical reaction. It's complementary to specific ligand. None of the above is correct. Yes, option B is correct. So it does not contains modified amino acids in both the cases. So whereas antibody antigen binding sites they only have specific binding sites, but they do not catalyze any kind of reaction. However, active site of enzyme they the catalyze the chemical reactions, and they both have complementary to specific ligands. And so option B is correct. A certain enzyme will
तो
hydrolyze.
लिगैंड नहीं हो सकता?
Yes,
Hello,
yes, yes.
the ligand
I mean, see,
can change the function.
no, they are means it is asking. Do you understand the question? Like question क्या कह रहा है कि एंजाइम का एक्टिव साइट कैसे डिफरेंट होता है एंटीबॉडी एंटीजन बाइंडिंग साइट से? उसका मेन डिफरेंस क्या होता है उनकी दोनों?
साइट से रिलेटेड।
यस। सो मेन डिफरेंस है कि उनमें
साइट
मॉडिफाइड अमीनो एसिड तो नहीं होते किसी में भी, राइट। और एक्टिव साइट
अच्छा।
एंजाइम,
वो
एंजाइम
और जो
एंजाइम
लिगैंड्स में जो चेंजेस आते हैं।
इट इज नॉट आस्किंग द चेंज इन लिगेंड,
ओके।
इट इज आस्किंग कि एंजाइम का एक्टिव साइट जो होता है वो एंटीबॉडी एंटी एंटीजन बाइंडिंग साइट से, जो एंटीबॉडी पे एंटीजन बाइंडिंग साइट होता है उससे कैसे डिफरेंट होता है। तो एंटीजन एंटीबॉडी का जो बाइंडिंग साइट वो स्पेसिफिक, एंटीबॉडी है जो एंटीजन, it's kind of ligand binding, so they have a complementary specific ligand site. Enzyme active site also they do have a ligand binding site, but they differ in term of antibody and antigen. They do not catalyze any kind of reaction, but they are just specific for the binding. However, enzymes they catalyze a specific kind of chemical reaction. You understand that?
Yes,
Okay, so option B is correct. So next is a certain enzyme will hydrolyze egg white but not starch. Which statement best explains this observation? Starch molecules are too large to be hydrolyzed. Enzyme molecules are specific in their action. Egg white act as a coenzyme for hydrolysis. Starch is composed of amino acids.
Enzyme molecules are specific.
Enzyme molecules are specific, yes, but egg white act as a coenzyme for hydrolysis.
But, sir, egg white itself is a protein, right? Then how it act as a coenzyme?
Yes.
Because coenzymes are non-protein part.
Okay. Yeah. Sorry, enzyme molecules are specific for their actions. So, you are right. This egg white act as a coenzyme. Coenzymes are non-proteinogenic, right? And in egg white, there will be it itself contain an enzyme that was lysozyme. So option B is correct. Yeah. Sorry for the confusion. So next we have which of the following statements is true about the region of the graph below where substrate concentration is much lower than Km. So for this part of the graph, enzyme concentration is greater than substrate concentration, or when substrate concentration is lower than Km, the initial rate is equal to catalytic efficiency multiplied by free enzyme or substrate concentration. So it is asking, let's write this. V naught is equal to V max the substrate concentration divided by Km substrate concentration plus substrate concentration. So it is asking that substrate concentration is way less than Km. So when S is equal to substrate concentration is way less than Km, the initial rate is equal to catalytic efficiency multiplied by free enzyme and the substrate concentration. So option B will be correct. So catalytic efficiency it will be substrate concentration and the concentration of the free enzyme. So option B will be correct. Okay. So next we have, which of the following is not among the six internationally accepted class of enzyme? Hydrolysis, ligases, oxidoreductase, or polymerases. So polymerases are not six.
Polymerases.
Yes, polymerases are not into the six internationally accepted class of enzymes. Enzyme X exhibit maximum activity at pH 6.9. X shows a fairly sharp decrease in activity when the pH scores much lower than 6.4. One likely interpretation of this pH activity is that glutamic residue on the enzyme is involved in the reaction, histidine residue in the enzyme involved in the reaction, or enzyme has a metallic cofactor, or reaction relies on specific acid base characteristics. So it will be a histidine residue.
It's B, histidine residue.
Yes, because once it will be goes down, this histidine it will be in protonated form, so it will not be active, right? So option B, right? Which of the following is true for the enzyme? First, they increase the rate of reaction by stabilizing the transition state. They raise the activation energy to shift the equilibrium to form a product. They lower the activation energy by altering the product of a reaction. So which one is true? Option A is true, only one. They increase the rate of reaction by stabilizing the transition state. Transition state. So option A is correct only. Okay. Next we have, okay, let's read little bit about again enzyme inhibitor. So enzyme inhibitor are two types. One other is reversible and this is irreversible. In reversible there is three type of classification: competitive, non-competitive, uncompetitive. In reverse irreversible it's active site directed and it's suicidal inhibitor. In this irreversible it comes into the covalent inhibitors. So a competitive inhibitor often has a structural feature similar to those with substrate whose reactions they inhibit. So there will be a competition between substrate and the inhibitor. So the structure will be similar, so binding to the enzyme will be similar. If the competitive inhibitor will bind, then substrate will not have a space to bind, and hence the inhibition will happen. So such as this antibody sulfonamide is similar to structure of aminobenzoic acid. So the sulfonamide is an inhibitor of aminobenzoic acid, competitive inhibitor. Non-competitive inhibitor, these are not influenced by concentration of substrate. It inhibits the binding irreversibly to enzyme but not to at the active site. So they also bind with the same affinity to the free enzyme and form the enzyme substrate complex and change the shape. of enzyme and active site. So what they do, first they go and bind this inhibitor and substrate. They will go and bind to the enzyme, and then they will change the, let's say this is the enzyme, and this is the shape of the active site of the enzyme to bind the substrate. So it will go and bind to the other side of the enzyme, and then they will change the shape of the active site. These are non-competitive inhibitor, but they kill the activity. So such as silver ions or heavy metals, they with thiol group in the side chain, group of cysteine residue in the protein chain. So these are non-competitive inhibitor. So if the cysteine residue is somewhere on the protein chain, which affect the way it folds into the tertiary structure, then altering this group could have an effect on the shape and act of the active site. So stop the enzyme from the working. Uncompetitive inhibitors do not bind to the free enzyme; they bind only to enzyme substrate complex to build the inactive ESI complex. So this uncompetitive is that they do not have compression between substrate and enzyme. They do not have okay, compression between substrate and enzyme. Substrate will come and bind to the enzyme and will give this complex enzyme substrate complex. But this inhibitor will bind to this complex and it will make it inactive. Further conversion from this to product will not happen. And this irreversible inhibitor binds at or near to the active site of the enzyme irreversibly, usually by covalent bonds, so it can't dissociate from the enzyme. So it is a covalent inhibitor. So in this there are two types: active site directed inhibitor, once the inhibition or binding will be to the active site, or it's a suicidal inhibitor. So active site directed inhibitor is also called a affinity label. It is chemically reactive compound that is designed to resemble the substrate of an enzyme, so that it binds to the active site and form a stable covalent bond when the susceptibility group of nearby residue in the enzyme protein. So there are multiple active site directed inhibitors. So one of them is, do you know what is the first covalent inhibitor? So first covalent inhibitor is aspirin. It is also a active site directed inhibitor, covalent inhibitor. The multiple covalent inhibitor, and there is a surge going on for the development of covalent inhibitor for cancer therapeutics. A suicidal inhibitor is a relatively inert molecule that transformed by an enzyme at its active site into a reactive compound that irreversibly inactivates the enzyme. They are substrate analogs designed so that via normal catalytic action of enzyme, a very reactive group is generated. The latter form a covalent bond with a nearby functional group within the active site of enzyme, causing irreversible inhibition. So next we'll be looking for the some antimicrobial drugs. So antimicrobial drugs classified as cell wall synthesis inhibitor. So cell wall synthesis inhibitor examples are beta lactams, penicillins. These are the examples. This penicillin is the first cell wall synthesis inhibitor. This These are the examples of beta lactams. This polypeptides. And another inhibitor kind of inhibitor is protein synthesis inhibitor, where they inhibit the synthesis of the peptides or proteins. And another kind of antimicrobial drugs are inhibitor of essential metabolites like folate. And this another kind of inhibitor or antimicrobial drugs are injury to plasma membrane. inhibition of nucleic acid replication and transcription. So these many kind of classified antimicrobial drugs are, because the classification is based on their mode of action, where do they bind, what do they perturb, which kind of action they take into the bacterial. So only bicyclic beta lactam show antibacterial activities. It's a true or false? Anyone of you? So beta lactam. Let's see the mechanism of the beta lactams. How do the beta lactam act? So they disrupt the cell wall synthesis, right? So beta lactam, they bind to the transpeptide. Transpeptide is active site. So beta lactams bind to the transpeptide active sites here, and then they inhibit this cell wall synthesis. So they block the transpeptide activity, disrupt the cross-linking and cell wall synthesis. So how do they react with transpeptidase? Transpeptidase, it has a serine residue into the active site. It will go and act to the penicillin. It's a beta lactam, bicyclic beta lactam. It will attack to the carbonyl. This bond will open. It will serine will be covalently linked to the transpeptidase. Serine, penicillin will be linked. It will inhibit this cell wall synthesis. So the question was, only bicyclic beta lactam shows antibacterial activity. The option is false. So here are the examples which have been shown that these many kind of bicyclic and monocyclic beta lactams, this monobactams, penicillins, pinams, this many beta lactams have been shown this antimicrobial activity, antibacterial activity. So option B is correct. And the question we have, consider the drugs amoxicillin and this chlorampheniramine. Which one of the following statements is correct? Is amoxicillin is bacteriostatic and chlorampheniramine is bactericidal, whereas the other option says reverse. Next option says both are bactericidal or both are bacteriostatic. So which option is correct?
Yes, A.
A. Okay. So antibodies can be divided in two groups on the basis of their effect on microbial cells through two main mechanisms, which are either bacterial or bactericidal or bacteriostatic. Bactericidal antibiotic kills the bacteria, and bacteriostatic antibiotics suppress the growth of bacteria. So keep them stationary phase of the growth. Okay. So answer B is correct. So amoxicillin disrupts the process of cell wall biosynthesis, and hence it is bactericidal. On the other hand, this chloramphenicol inhibits protein synthesis by binding to the 50s subunit, 50s ribosome subunit, and thus it's a bacteriostatic. It do not kill the bacteria. So option B is correct. Fine. So option B is correct. So here the amoxicillin structure is given. The main difference between amoxicillin and penicillin is that amoxicillin is effective against wide spectrum of bacteria compared to penicillin. Both amoxicillin and penicillin belong to class of antibiotic called penicillins. So they both have beta lactams. and disrupt the cell wall synthesis by binding to what? Active site of transpeptidase. This chloramphenicol is an antibacterial agent with broad spectrum activity against gram-positive bacteria, gram-negative bacteria, and its mechanism of action is by inhibition of bacterial protein synthesis by binding with ribosomes. Major toxicity comes from is hematological. Okay. Next question we have: which of the following statement is correct? This clavulanic acid is an irreversible inhibitor of transpeptide enzyme. Amoxicillin is an irreversible inhibitor of L-alanine racemase. This clavulanic acid is a suicidal inhibitor of serine-based beta-lactamase enzymes. Amoxicillin is a reversible inhibitor of serine-based lactamase. So the option C is correct. This clavulanic acid is suicidal inhibitor of serine-based beta-lactamase enzyme.
अरे मेडिसिन केमिस्ट्री नहीं है रिलेटेड टू मेडिसिनल केमिस्ट्री बायोकेमिस्ट्री
Yes. Hello.
इज इट इज रिलेटेड टू मेडिसिनल बायोकेमिस्ट्री
Yes. So biochemistry. I mean the courses. If you go into the deeper into biochemistry, so it will come down to the medicinal chemistry. So these are class of enzyme inhibitors,
ओके
right? So it is related to biochemistry. Okay.
Sir, is this type of question will be asked in the final exam?
Okay. So final exams. I need to see the. I mean the final content means last time I taught this organic chemistry in biological system. So this kind of exam, these kind of questions are same. And once I see the syllabus, so syllabus of both the uh, courses are same, means similar. So I guess there can be questions.
सर right now sir penicillin is derived from fungi kingdom fungi
Yes, yes.
this is all I knew
Yes. So first.
penicillin comes from fungi
Yes, so at the level of chemistry, right? So it's a organic molecule. If you see at the chemistry prospect, right? So it's organic molecules and how it acts. So it comes into this kind of courses. So if you see the medicinal chemistry, biochemistry, organic chemistry, and biological molecules, and more likely chemical biology. So these courses are having similar kind of syllabus. Okay, so okay, so let's stop it here, right? Thanks a lot for joining today. So next session will be meeting next week, and if you have any doubt, further doubt, you can email us. We'll